Hello, welcome to the fifth pre-recorded lecture for Math 155. Last time I talked about matrices. Today I'm going to be talking about how we can apply matrices to solve different types of problem. So today I'm going to start by talking about where do matrix equations come from. So these are certain types of equations. And then I'm going to talk about how we can use matrices to solve linear systems of equations. Now, you have met linear systems of equations before, so I'll talk a little bit about that. And the second type of problem we can use matrices for is to evolve vectors forwards, and these are really important for when we want to do certain types of population model. We're going to talk a bit more about these in the problem classes and more about the second type next week. But I'll be focusing on linear systems in this particular lecture. So have a brief read of this outline here before moving on. Okay, so we say that a linear system is any problem that can be written in the form AX is equal to B for some matrix A and vectors X and B. And depending on what type of problem we're trying to solve, our unknowns could be in our matrix X or our vector X, sorry, or in our vector B. And we say that this is a linear problem because all of the unknowns in our vectors X or B, depending on the type of problem we're solving, appear linearly. So that means there aren't things like X squareds and Y squareds in the components of our vectors. So for example, if we have a system of linear equations like 2x minus y is equal to 3 and x plus y is equal to 4, then this is a linear system in x and y because we don't have terms like x squared or xy. So this is a linear system, and what we're going to talk about today is how we can write this type of system here as a matrix equation in the form AX is equal to B, where our vector of unknowns X is equal to the vector XY. So as I mentioned at the start, there are two types of systems, two types of linear systems that we're interested in solving using matrices. The first is of that kind of system of equations that I just had up here, 2x minus y is equal to 3, x plus y is equal to 4. That's a system of linear equations, sometimes referred to as simultaneous equations. And the second type is the evolving vectors that describe some change in states, so that describe states or populations. So I won't be talking too much about these today. I'll talk about them more in upcoming lectures and problem classes. These are really important. For example, if you've got a population at a particular time point now, can we describe how that is going to be, what that population is going to look like next year or the year after, and so on. The setup for both of these is quite similar, and they both require us to form linear systems. So to give an example, you would have met problems like this before, I'm sure. For example, Julia buys 2 tomatoes and a fig for $5, and Maurice buys 1 tomato and 4 figs for $6. How much do tomatoes cost? How much do figs cost? So if we want to solve this type of problem, we can use a process of elimination. You rearrange for to get your equations in terms of figs and then substitute it in, do things like that, doing some sort of mechanical operations on these equations to ultimately get them in terms of the cost of figs, and then you can work out the cost for tomatoes or vice versa. Okay, so let's set this up as a system of equations. So if we let t be the cost of tomatoes and f be the cost of figs, then we can write this down as 2t plus 1f is equal to 5, and that's because Julia bought 2 tomatoes and 1 fig for $5, and because Maurice bought 1 tomato and 4 figs for $6, we can write that as 1t plus 4f is equal to 6. Now, ordinarily, we wouldn't put the ones down there, but the reason for that will become clear in just a moment. We can see that we've got our T's aligned here and our F's aligned here. So we can just use the rules we know about scalar multiplication for vectors to rewrite this as T, so T is now our scalar here, times by a vector 2, 1 plus F times a vector of 1, 4 is going to equal another vector 5, 6. So all that's going on here is we're saying, okay, if we take this, let's do it in blue, if we take this first row here, because the components are independent, if we do 2t plus f is equal to 5, that's exactly the same as what we would get on this first row here. And likewise, we can get the second row. So this vector equation is just another way of writing down those systems of equations that we had above. And because we can manipulate vectors in various different ways, we can write this as a matrix equation as well. So if we think about the rules of matrix multiplication that we learned last time, we can write this as 2, 1, 1, 4 as by TF is equal to 5, 6. So if you go back and look at the rules for matrix multiplication that I discussed last time, all this is saying here is we're saying, we go, remember, across the rows and down the columns. So we do 2 times T and add that to 1 times F, and that gives us 5. Likewise, we'll do 1 times T plus 4 times F, it's going to equal 6. So this is just another way of writing down exactly the same information we've already had, but this time as a matrix equation. And so if we call this matrix A and this vector here with the T and the F X, and this matrix on the this vector on the right hand side B, then we can write this as AX is equal to B. And that's our matrix equation. So all this is doing is rewriting our linear system of equations into a matrix equation. And this ultimately has certain advantages. Whilst we've got, say, these two systems of equation, or two variables here, two unknowns, it's relatively easy to solve. But if you have many equations, if you say got 1,000 unknowns, it'll be very difficult to solve. We can solve them much easier using matrix equations. So that's the first type of problem I talked about, this problem where we're trying to solve linear systems. The second type of problem that involves matrices, that I said, was evolving vectors that describe some sort of state or population that's changing over time. So the second type here, to give an example of that, suppose we've got some population here, it's a population of bears, and in that population of bears, there are some juveniles and there are some adults, and we can say, okay, let's suppose that Jn, so J with the subscript n, is the number of juveniles in year n, and An is going to be the corresponding number of adults in the same year. And we've got some rules about how the population changes. So, for example, here approximately half the bears, so approximately half the bears are female, and each adult female has approximately 2 cubs every other year. And then each year, 25% of juveniles mature into adults, and 10% of the entire population dies. So what we can do is we can start writing down a system of equations. So if we think about, we know what the number of juveniles and adults is in year n, what is going to be the number of juveniles and adults in the year n plus 1? So j, the time point n plus 1, year n plus 1, is going to equal, well, first of all, we're going to have the proportion that survive of Jn, and we're going to have to subtract the proportion that mature, and then to this we're going to add the number that are born. So what does that look like? Well, we know that each year 10% of the juveniles die. So we know that we're going to have 0.9 Jn surviving to the next year. We know that 25% of them are going to mature into adults. So we need to subtract 25% of them, so 0.25 is the proportion that we'll be taking away. And then the number that are born, well, we know that approximately half of the bears are females, and each adult female has approximately 2 cubs every other year. So on average, that means that each year, each adult is going to produce on average half a cub. So throughout all of this, obviously we can't have half a cub, we can't have 0.26 juveniles or whatever numbers we end up on. These models are all about averages, and they're thinking about are the populations growing or shrinking? Because that's obviously really important from, say, a conservation perspective. Is this bear population growing? Is it stable? Is it shrinking? These types of models will tell us that, but we don't care about if there is 0.26 of a bear. We would usually just round that up. I mean, we're interested in what's called the qualitative behavior of these models. So on the end here, because of, on average, each adult female has approximately 2 cubs every other year, and on average, half the bears are female, we say we have plus 0.5 AN is the number of juveniles that are born in the year n+1. We can do a similar thing for our adult equation, which is AN+1. We say about 25% of the juveniles mature and 10% of the adults die. Therefore, this equation is going to be 0.25 times JN. So those are the juveniles maturing, and 10% of the adults die. So approximately 90% survive. So 0.9 AN survive. So taking those equations that we've got there, we can, first of all, collect the terms that we've got together. So I'll go back up here a second. We had 0.9 JN minus 0.25 JN, which is just going to be 0.65 JN. So if I write this down here as JN+1 is going to equal 0.65 JN and 0.5 AN. And here we've got 0.25 JN and 0.9 AN. So all I've done there is just combine the JN terms that were in the previous equation for JN+1. And again, just as before, we've got our JN terms here and our AN terms here are grouped together and then multiplied by some coefficients. So that means that we can write this as a vector equation. So we have JN+1, AN+1 as a vector on the left-hand side here. And we can group our coefficients for JN together. So if I write this as 0.65, 0.25 times by JN, and add this to a vector of 0.5 and 0.9 times AN. Then again, this is going to give us exactly the same as what we had above, just like we had in the example for tomatoes and figs previously. And just as in that example, we can then write this as a matrix equation using what we know about the rules for matrix multiplication, that the first column of this matrix is just going to be the first column, this first set of coefficients up here. So this becomes the first column of our matrix, 0.65, 0.25, and the second column is going to be this set of coefficients here, 0.5, 0.9. So that's our matrix. And then our vector on this side is just going to be JN, AN. So if this is our matrix X, our vector X of unknowns that we want to find, in other words, the unknowns we want to find in the next year, what is the population going to be like in the next year? We know what it's like this year, so that's our vector B, and then this is our matrix A. This gives us X is equal to A times B. So this is similar to the first problem that we had before. We had AX is equal to B, where X is always here our vector of unknowns that we're trying to find. So we know what B is, we want to find X, and we know what A is. So the previous problem was set up as AX is equal to B, and here we've got X is equal to A times B. And the first problem is actually a little bit easier to solve, those systems of equations, and that's what I'll focus on today. We're going to come back to problems like this in future. Okay, so let's go back to our example of tomatoes and figs. That was an example of a linear system of equations that we want to solve. So how do we solve a problem in the form Ax is equal to b, where x is our vector of unknowns? So if we had scalars, if we had a, x, and b all being scalars, just regular numbers, we would, and x is our number that we want to find out. We don't know what it is, it's some unknown. Because we know a and b, as long as a is not 0, then we could just divide through by a, and so x would equal b over a, and that'd be it. It'd be very straightforward. But what about matrices? Well, this is a little bit more tricky because we can't divide by matrices. Okay, so the reason why is 1 over a makes no sense. Okay, so 1 over a makes no sense for matrices. Why is that the case? Well, if you were to think about doing b divided by a, where b is a matrix and a is a matrix, well, is that 1 over a times by b, or is it b times by 1 over a? In other words, are we multiplying b by 1 over a on the left or 1 over a on the right? And you don't know that. So that's one of the reasons why dividing by a matrix doesn't make sense. So this is a big no-no, you don't do this. So ignore that. So how do we do it instead? Well, we use something called inverse matrices. So what we do is we solve our matrix equation Ax is equal to b by finding a matrix capital B, so that we have b times by a times by x is just equal to x. So b is a special matrix in relation to a, and when we multiply on the left-hand side by of ax by b, we just get x on its own. And because of this, if we multiply the left-hand side of the equation by b on the left-hand side, we need to do exactly the same to the right-hand side of the equation. So we multiply little b by capital B. This then gives us x is equal to capital B times little b. In other words, we've multiplied here by b and here by b. And because BA times x is equal to x, we just end up with x is equal to b times b. So that's a matrix B times by a vector little b. And we say that this matrix B is called the inverse of A. And we write this as a to the minus 1. So like I said, we don't ever write 1 over a for a matrix because that doesn't make any sense, even though when we would maybe think of a scalar to the power of minus 1, that means 1 divided by. You always just write a to the minus 1 as the inverse of a matrix, but you never write 1 over a. So this inverse matrix is really important, and before talking a little bit more about that, we need to learn about something called the identity matrix, and this is a very special matrix as well. And this is a matrix where every element except for the ones on the main diagonal is equal to 0, and every element on the main diagonal is equal to 1. So the main diagonal is just the diagonal that goes from top left to bottom right. So it's usually denoted by I, or sometimes if it's an n by n matrix, because it's always a square matrix, if n is equal to 2, then it would be I2. If n was equal to 3, it would be I3, and so on. So I2 is just going to be 1, 0, 0, 1. In other words, we've got ones down this main diagonal from top left to bottom right, and everything else is 0. And if we have I3, then this is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So again, everything on that main diagonal from top left to bottom right is equal to 1. Do that again. All of these entries here on that main diagonal are equal to 1. Everything else is 0. Why does this matter, and what's the relationship with the inverse? Well, this identity matrix always satisfies I times by x is equal to x for any vector x. It always satisfies as well I times a is equal to a, or a times by I is equal to a. So whenever we multiply a vector on the left by the identity matrix, then we get the vector back again. whenever we multiply a matrix by the identity, whether it's on the left or the right, we just get the same matrix back again. And this is just like in scalar multiplication when we multiply something by 1. When we do 1 times by 2 or 1 times by pi, we just get 2 or pi back again. Okay, so there's this really close relationship between the identity matrix and the inverse of a matrix. And that's because if we have a square matrix A, so the matrix has to be square, and another square matrix B, the matrix B is called the inverse of A if A times by B is equal to the identity, and also we have B times by A is equal to the identity. So these identities have to be of the same dimension, which is why we have to have square matrices. And as I said above, we denote the inverse of A as A to the minus 1, but this is never 1 over A. We never write 1 over A for a matrix. So what if a matrix doesn't have an inverse? Well, if a matrix doesn't have an inverse, then we say that it's singular. So a square matrix A, which doesn't have an inverse, is called singular. And a matrix which has an inverse is called invertible or non-singular. So the question is, how do we know whether a matrix is invertible or not? And recall, the whole point of doing these inversions of a matrix is to solve our linear system of equations. So if we can do this inversion, we can solve that system of equations. So we want to know whether we can solve that system of equations. And if a matrix is singular, then we can't find its inverse, and so we can't solve that system of equations. So if we've got a 2 by 2 matrix A, which is given by the entries A, I, J, where I and J are just the ith row and the jth column. So this is Aij when I and J are both equal to 1. The determinant of A is called det A in brackets, and that's just equal to A11, A22 minus A21 times by A12. So all that's saying is we're going to multiply this element by this element, and we're going to subtract the product of this element and this element here. And then if this determinant is non-zero, then we can say that the inverse of A, which if you recall is given, is denoted by A to the minus 1. So here we have 1 over the determinant of A, which is just A11, A22 minus A12, A21, assuming that's non-zero. And here, what we do is we switch the order of our main diagonal elements. So this here becomes A22, and this becomes A11. And then we take minus A12 up here and minus A21. So that should be a minus there. So the elements on the main diagonal switch place, and the elements on the off diagonal are, we just take the negative values of them. Okay. So if det A is equal to 0, then we've got a 1 divided by 0, and that's why we can't find the inverse of A. So in that case, we say that A is singular. Okay, so that's how we find the inverse of a matrix. Now let's apply that to our problem where we had tomatoes and figs earlier. So recall that we had 2 tomatoes plus 1 fig is equal to $5, and 1 tomato plus 4 figs is equal to $6, and we can write this as this matrix equation up here at the top. So to solve this, well, first we can, let's write this as AX is equal to B, where this is our B, this is our X, and this is our A. The first thing we need to do is we need to find the determinant of A. So that's going to be the product of the elements on the main diagonal, so 2 times by 4, minus the product of the elements of the off diagonal, 1 times 1, which is just going to be equal to 7. Yeah, so that is non-zero. That tells us that our matrix A is invertible. So now we can construct the inverse according to the previous slide. So we take our determinant, so we do 1 over, this is 1 over det A. I've calculated above, so that's going to be 1 over 7. And then we do these operations on the elements within the matrix. So this is going to just be equal to 1 over 7 times by, let's flip the elements on the main diagonal first. So here we're going to have 4, here we're going to have 2. And then we take minus the elements of the off diagonal. So we're going to have -1 and -1. So this is our inverse a to the -1. And you can do the check yourself. If you calculate a times a to the -1, that this is also going to be equal to a to the -1 times by a, which is just going to be the identity matrix I, which is 1, 0, 0, 1. So you can do that calculation yourself just to check. So if we multiply on the left-hand side both of the sides of our equations by a to the -1, in other words, we had ax is equal to b to start with, and we're going to multiply this by our inverse of a on the left-hand side. Then we'll have this equation here. So this was our inverse of a here. So this is a to the -1. This is a. This is our x. This is a inverse again, and this is our b. So if we calculate that, then we're going to have here, we're going to have 1/7 times by 7, 0, 0, 7. So 1/7 is just a scalar. So when we multiply these two things together, we're just going to have the identity matrix here on the left-hand side, times by TF, our vector of unknowns. And that's going to equal 1/7 times by 14/7, not over 7, sorry, 14 and 7. So this is just A inverse times by B. So we've got the identity matrix here, 1, 0, 0, 1 times by TF is going to equal 2, 1. And because the identity matrix times by anything is just whatever that thing was, this gives us TF is equal to 2, 1. So tomatoes cost $2 and figs cost $1. So this is a really great way of being able to solve linear systems of equations, because although it's, like I said, might be straightforward to do elimination when we've just got two things here, if we've got many, many unknowns, then it becomes very difficult to solve these equations. We can find the inverse of larger matrices. It's a little bit more complicated. We're going to focus here just on these 2x2 systems. Okay, just to finish today, to just illustrate what is going on here when we are trying to solve these systems of equations. So suppose we've got these three different systems of equations, and this first equation is just going to be the same in all of them, and then we're going to vary the second one. So this 2x plus y is equal to 5. Well, we can write that as y is equal to 5 minus 2x. So that's going to look something like this. We can write this as y is equal to 3/2 minus x/4. So that's going to be another line going something like this. These are supposed to be straight lines. I just can't draw straight on here. And there's some intersection here, and that value here gives you the solution to this set of equations. So that point there is going to be our solution. What happens if we go into the second example? So if we've now got 4x plus 2y is equal to 10, well, if we rearrange this, then we're going to get y is equal to 5 minus 2x. Well, that's just exactly the same equation that we had before up here in red. So that means that our pink line is going to completely coincide with our red line. And what this is saying here is we've not got any new information from our second equation. So if you go in and buy, in this case, say 2 tomatoes and 1 fig, and that costs you $5, and someone else goes in and buys 4 tomatoes and 2 figs, and that costs them $10, all you've done is you've just doubled everything. so that you haven't got enough information in the system to work out how much a tomato costs and how much a fig costs. So this is an example of, in this case, the matrix would not be invertible, its determinant would be 0. And the reason would be is because we don't have enough information to solve it. So it's consistent, but we just lack information to be able to solve the problem. And then finally, if we look at this case here, in the green scenario over here, we've got y is equal to 5/2 minus 2x. And that will look something like this. And the problem here is that these two are parallel. So in this case, there's no intersection between those lines, and so there's no solution to this system of equations. And they've got the same gradient, which is why they, but a different intercept, whereas in the previous example, they had the same gradient and the same intercept, so they were exactly the same line. Here, the line has been shifted. So there's no intersection, so there's no solution to this set of equations. That means that our system is inconsistent. So in this case, again, the determinant of this would be equal to 0. You can, I suggest you go and check that. The reason being, okay, well, if we use the tomato fig example again, someone's gone into the shop and bought 2 tomatoes and a fig, and it's cost them $5. Someone else has gone in and bought 4 tomatoes and 2 figs, and that's cost them $5 as well. So the person on the checkout has maybe made a mistake and they charged them the wrong thing. You can't solve these equations. You can't work out how much a tomato costs and how much a fig costs because these equations are inconsistent. And so graphically what's going on here is those lines are parallel, so they never intersect. Okay, that's it for today. There are some self-study questions at the end. Make sure you're familiar with all of these terms. What is a linear system? What's an identity matrix? What does it mean for a matrix to have an inverse and to be invertible? How do we calculate that inverse? What does it mean for a matrix to be singular or non-singular? And how do we work out what the determinant is? What does that mean? So have a go at those, and I'll see you at the problem class. Thanks very much.